Okay, this demo is using Crackme um, to illustrate to you how to patch a binary so that you can bypass the program logic to get your result. And another purpose of this video is try to show you how to use the tools for reverse engineering of Windows binary. One of the tools is this disassembler IDA tool. I don't have time to teach you how to use the tool exactly. I hope this video give you some guide so that you can follow how to use IDA tool, how I use the IDA tool to do my daily reversing activity, or if you want to use the debugger so that you can trace the instruction by instruction so that we can get the result from the processing by the caller program to call you program. By the way, caller program, call you program to have some kind of functional log start from the changing um, the stack pointer, increasing the the stack pointer with space to hold the data without overwriting anything, uh, uh, prevent the program to go back to the caller program after the return running of the call you function. And yes, this is the main purpose of this demo. So we picked the Crackme, and Crackme is a simple program to ask the user to type in something, and then we will go over the caller and call you program by changing the stack pointer. Here is one example. If you never talk with the information provided in the disassembler or the debugger, you may see the CPU instruction code. Uh, to best way to learn the instruction code, try to grab the basic concept and then put a binary inside either disassembler or debugger to understand it by moving in the instruction per instruction and get back the result. And you can monitor the result, what happening in the debugger windows panes. So this is example move the pushing, just like I explained in the class. When we have a couple of books in the bookshelf, if I put book number one onto the table, then it's just like pushing something onto the stack. And then if I grab the book number two, put on top of the book number one, the same thing is doing by pushing another information to the stack. After everything, we can pack the book and send to some other people. Then this is also some kind of energy illustrative example when the caller program push the parameter or argument to the stack and then make the call. Once it makes the call, if you want to see the result, you better check the EAX register in Win32-bit environment. If the size of the result can sufficiently be kept inside the register with the size 32-bit size, so all the result will be right there. If that need to be a larger size, a buffer usually create a particular location in the heap area, and the EAX register will only keep the pointer pointing to that address. So let us go to do the reversing, and we try to do a patching and then say the call me function. That is again. So before we go to this frame stack illustration, let us go to the virtual machine. Okay, we are in the virtual machine, and uh, I have go back to my snapshot. So go to the sample and find the Crackme, and then copy the Crackme to the 10 folder. For the PE structure, you can do it by your own self. Now I go to the command prompt and try to run the program. So I go to Crack. Once I type it, the message palm out, I need to type the password. If I type the correct password, 1 2 3 4 5 6 7, I get a result configuration. If not, I type the 9685465. It is incorrect. And then I need to type it again, and then the loop will go over until everything is okay. So that is the program, so simple. So if you want to understand more about the source code, you can find it in the in this in the sample location. Crackme is not malware, so that it is not shifted with password. So here is the C program. You can open it by different kind of editor. Now you can see the program source. It's straightforward. I don't need to explain too much for experienced programmer. So now, if we want to analyze it, first of all, we do it in the basic code chat. I skip this part. Now I want to put it inside the debugger, disassembler. We use IDA poll. When starting the IDA poll, it will recognize the basic information right here because this is a PE file, so it does show us the information of PE file, and then it runs quite quickly because the size is not so big. So basically, when the IDA poll start, we have a couple of things we can do. First, we find the start location, and then usually click the core. Whenever you see these things in pink color, that is the system library. Usually we don't take care of system library. So the first call is 84033CC. Double click it, go to that location. If I want to go back, escape, go in. Okay, here we see also I click the core, pink color locator. It will go to 403983. So 3983 have another call, nothing else, and go back, escape. Then see if I can find any other location. Another one's the end of the 4033. Well, other than that, we can try to use course reference 2. It's from top to this location. Can I find course reference from? It goes to another 403983. So 3983, where's the 3983? Yes. This is the page we listed before. We can also course graph to and also graph from. Just hit allocation. So nothing interesting. I go back 2 level, go back to the start, see whether there's some other thing I want to see. What is 4039E? And 139E, we can find 403611. Still, I don't see anything that attract me, or maybe some more information you need to know. Okay, so sometimes by checking this block, finding code may not allow me to find the hints for me to do the analyze of the binary in a quicker way. So now I go to another way to identify important function we need to address with. For example, I go to view and then I go to the strings. What kind of string? What kind of strings we need to address? Of course, password, congratulations, fail, error, something like that. So if I want to find I find the input password, incorrect password, congratulations. So if I pick congratulations or password, see what I can find. Here is in the this data section. If I double click, it put me to the link that will call this data. And this is also the data only. It don't show you the content of the nicely presented functional block diagram even in the view A. However, if we find this, if we find anything in this blue in color that is the course reference. So if I click this course reference, see if I can find the content of the congratulation. I don't see it. I only see 1, 2, 3, 4, 5, 6, 7, which is global uh, memory, global variable. So I go back to my data section by hitting escape, and I check the other one below this configuration. So I have been put inside another function. This function, I can find piece input password, the same command that we get it from the command. And then there is a branch right here, either correct or incorrect, and then congratulations. What we have to do is try to forcing this branching instruction uh, don't go too wrong. Before that, it must be some kind of way to do the string comparison. You remember the source code, compare the global variable of uppercase password with the data entered by the user through the keyboard scanf function to gather the input as lowercase password and then compare these two variable byte by byte. If everything is okay, it will go here. You should be okay. So what we have to do is try to find the branching. I don't care about what kind of checking about the information. The branching, we don't know the CPU instruction code, but basically we can guess JZ. That means jump equal to 0. If not 0, go to here. 0 is right here. So the simplest way is try to modify the JZ into jump JMP so that whatever information outcome, it will jump here. Okay, so what is the address right here? I click this, go to space bar. You will be able to find the flashing icon right here at the address 40106E. Let me copy it down. I open a text editor, paste it right here. Okay, I need to set a breakpoint right here. What else? I want to see some more things. For example, there's another job and that will be returned. All of them will be returned. How about I just keep something right here? Another big point in this branching statement. This location address should be able to find by hitting space bar. And that is another big point I want to set because I don't want to go to the return back to the main start program. Otherwise, it will have problem to close everything and terminate the window. So I have two district one, but I still want to keep the current location. I want to check. And last but not least, if you want to find the important function, you want to see how the program flow, you still need to double check the course reference to diagram, or you can check the course reference from diagram. Now you have a better picture of the from and more information right here. You see a lot of functions calling even though the source code is so small. So I tell you every time when you see the pink color, you don't need to analyze because this is the system library. So, but we already find the most important part. Bear in mind, we are first try to find each cross-reference from and cross-reference to correlation of the calling caller to the callee. But this one, yeah, I don't want to find it, go through this kind of tedious process. Instead, we just go to the strings to find the relevant string and go to that location to find the important functional block that we want to analyze. So but in analyze some other sample, maybe you need to find using cross-reference from or cross-reference to identify the key function you want to identify for your work. So let me put the Crackme into the debugger. Here we put in the 96 dbg. It will automatically select the right one for you. Okay, I have the window create here. I want to see my breakpoint. I mean the expected breakpoint put inside the notepad. The first one I want to set in debugger. This is the CPU pane. This is register. This is the some kind of standard code reference. You see ESP plus 4 means the 4 byte before the ESP. You can find this information plus 8. You can find this 8 information plus C. You can find this piece of information. And then you will see this is stack, this is the DOM data. Sometimes here you can find EX register, some value right here. But currently we are in the mtdll.dll. What we have to do is go to the user code. Now we are at the user code address of 401298. So how can I set a breakpoint at the address 401060? Let me enable the hotkey. Don't know why, but maybe because I turn on the debugger. Let me kickstart this first. Yeah, just cover it. And then I kickstart the zoom first. Yeah, after zoom it, then I can run the Win32 DBG, then find the recent file crack. Now we have everything ready. So nothing right here. We're in the mtdll.dll. We go to user code. So we start at the user area with the RVA of 1298. Now we need to find our address. The address at the location of 40106E. Then I copy this information and then I want to go to that address to create a breakpoint. How to do that? We click Ctrl-G and then copy that piece of information right here. If you find that a screen that is addressable memory location of this region, so I click OK. Now you can see the branching. It looks like the branching will go to right here and then go to call this, and that includes the congratulation message. So I set the breakpoint here by double click it right here. Okay, if you are using Windows keyboard, you can hit the function F2. That is one way you can do it. Another way is you can type the command. For example, if I want to set another breakpoint at this address 401097, so I can type command BP means breakpoint. If everything is okay, you will see it's okay. Then I go to big pond, and there's two big pond here. This information match to each other. Okay, so what is the next? Let me go to the original location, see if escape okay for me. It doesn't work. How about control escape? Don't know. It doesn't allow me to go back to my origin place. Then I will click one button called step over. It just from the ESP. Oh, I can actually use the ESP to go to the take this to the right location. For example, I go to here. Yeah, yeah, I can. Later on, whenever you want to go back before you hit step over, you can click the EIP to get back to your location. The first instruction is 55. The 55 is 1 byte. That means push EBP only require 1 byte. Then we already push EBP. So EBP before I click the step over is coming with the address of one with the content of 19FF80. So push EBP to the stack, that means the stack are pushed. So the EBP 19FF80, the value of this EBP has been put onto the stack. That means in our example, the book called 19FF80 have been put onto the table. Now we move ESP to EBP. We push this here because we need to change the base pointer with the stack pointer. So if I execute this instruction at the instruction pointer location, the ESP, the content will put it here, not to the stack. Push will go to the stack. Move, it just moves from one register to another register. So you pay attention. If I click step over, yeah, you see these two are the same. Okay, so now let us go back to the frame slide and then come back later. You may be able to find some more about the stack. Well, sorry, I jumped a little bit. Let us finish the patching study, and then we go to the frame study on the changing the start pointer by referring to the slide. So what we have to do is, yeah, we already have two breakpoints. Let us run to that location. Click run. Now we see piece input password. Then it is running because the window the command prompt require us to type in something. Let us type the wrong answer. Then you will see it stop at the first breakpoint, which is the branching. Now the branch set, it won't jump into this location. It's jump not equal, but I want it jump to here. So how can I change this information? The bytes right here, the instruction byte is 74OF. It represents jump equal to this address. So we right click right here, go to assembly. Okay, go here, right click, assembly. Then we change the jump Z into JMP. Okay, we change this one. Don't change anything behind. So we change it JZ, JMP. If everything's okay, instruction encoded successfully, and if that is green, if that is red, you better pay attention. Sometimes different code may provide different, for example, 74 may referring to jump equal whatever, and then 64 may equal to push, and E8 is a call, and you will see the argument or the opcode is 74, opcode 68, opcode E8, usually expect some opegram. The operam may have a larger size so that when you do the sample patching, sometimes it may warn you, because the instruction you input may not equal to the existing byte size. But this one should be okay. You see, I only changed the EB from previously. I don't remember, but later we can check it later. So once we do this, we move back to the instruction pointer. So you see it's jump now. Then if I take a step to step over, yes, it is jumped. So it will push some more thing and make a call to a function. Usually I think it will print out some statement. Yes, you see the configuration right here. That means I'm okay. I already be able to run this program without typing the correct answer. So that is not complete because the patching only in the virtual memory only. I want to save it, the anything I change to the file so that I can run it again and I type anything I can get past without typing the correct password. So how to do the patching? We need to go to right click, go to patch. A Windows come up, you will see the patching changing from opcode 74 to EB. Sometimes you patch a lot of things. It will show you some other items or entries right here. You need to check all of them to make sure your modification is perfect. So a patch a file, you cannot save with the same file name because the current file have been handled, assessed by the x32Dbg. So there's a handle right there. It will Windows will forbidden you to do any modification except read. So I set whatever for Crackme. Then I save another file. So I can safely create the things right here. Now I go back to the command prompt and try to see run the program Crackme. Have anything, I got configuration. So that is the way I crack the file and teach you how to do the assembly, a branching statement or modify some other things, and then patch it and save to a new file for our further analysis. Now let us go back to the stack frame pointer because I'm using Crackme as also an example to show you how the base pointer statement have been changed in the slide. Let me go back to the slide. Okay, now on the screen you may be able to see my slide. So that is interactive slide. I try to explain through the slide without accessing the VM first, and then we parallel have the slide together with the x32Dbg section on Crackme on the exact location. You can see the interactive movement. So the first thing, basically, this this slide, a couple of slides with the purpose to show you what the instruction be executed and how it changed to the step pointer. So before we start, we find a good example in a particular location that the EIP at the address of 40188D. So at this location, the instruction will say move ESP. We want to demonstrate move ESP. So the current location, the return address of the caller function will call to 14FB14. Then the next slide will see, you see the EBP location right here. The content should be keep it right here on this side. it runs from the higher memory to lower memory. So whenever you see subtract the base pointer means it's moving down or up or increasing the size is using subtract. So here you will see when we move in, then the first instruction is push EBP to some location. The EBP previously is in the return address. The base pointer is moving one step forward. You see? Okay. And then the instruction pointer is plus from XB to XC, one item. So Y is simple because this is instruction pointer. So let's see another step. Another step will be move ESP to EBP. ESP is right here to EBP. Okay, we move the ESP to EBP. Then we see that the instruction pointer move from XC to XE, all because here the ESP EBP move require 2 bytes to hold the opcode. So we move the EBP in ESP in this location and put in the same base right here. And then 2 pointers pointing same location with the current content containing this address is 14FF10. If you see the interactive under the demo in the VM, under the x32Dbg, maybe the address is not exact 14, maybe 19. I don't know, maybe some typo error or maybe a different version of Windows. So I prepared this slide a couple of years ago. So just neglect the exact content right here. But basically, the structure of moving the ESP, EBP at the same location will be the same. So next instruction, we need 6 bytes because the size of moving, try to do a subtract of ESP, that is ESP in black color. We need to create a buffer, make sure we have some space right here. The space size is 1C4, larger increment. But the increment in the command line, the instruction command line is subtract. Subtract ESP, that is the red in color. To subtract, it means increasing the size from this to this. So the next step, you will see this moving down the content. Don't know whether it changed or not. So we see how the slide be presented. Oh, the content is still right there, but the content at the ESP address content will change, and the ESP EBP will keep on don't move condition. So why EIP change? Because different opcode size will be different. This must be the size increase may representing the opprogram with 4 bytes and then instruction points 1 byte. So let us show it in the virtual machine by the tool that we are holding the Crackme and find the right location, and then we go back simultaneously by moving the slide along with the step over instruction so that you can compare what's going on with the same window. Let us move to the virtual machine. Now I give you a picture of my full window. Now you're supposed to be able to see my debugger and the slide. But I need to find the right location in the debugger first. Now we are ntdl.dll, we go to the user code, but I don't know where is this code relies. But the instruction pointer may give us a very good idea. So that is 4018 1A8B. Now I need to, before I do anything, I need to remove the previous breakpoint. Select that and then we'll move. How can I go to a particular address? Control G in debugger, G in disassembler, G in idable, Control G in x32Dbg. So I click here and Control G and I type 401A HD. Yeah, this one. See if I can enlarge a little bit to make sure I'm correct. Yeah, this one. And this. I click OK. I go to this location, and that is 55 and 8B. You'll see push EF, push the instruction is push EBP. EBP, you push here, and something like that. Let me set a breakpoint here on how about we just go a little bit backward. What is the caller function? This is call E function. Can I find the caller function? The answer is yes. Let me pause my screen and go to the IDA code. I want to find the caller function of the 1A, B, 8B. Okay, I want to find out the caller function. We'll call the call function at the location of 4018B. So I go to the IDA poll window. Let me go to the address. Then I type G 4018B. I will be put into this location. This is the address of 4018B. Then what is the caller function? One of the ways is find right-click to cause reference to. It should be on 401252. Other than that, we can use another features built in the IDA poll. We hit space bar, go to test mode. In test mode, you will see the cross reference link. If I double click, I go to the location that calls 4018B. Then what is the address right here? The address 401260. So I make a copy right here. Then I go back to the notepad to keep a record right here. I need to go to this location, set a breakpoint, starting from here, and then jump into 4018B. So let us stop and moving our screen in a proper way. Now we have our main window with two part. One is the slide, and another is the x32Dbg. Now we already know the location, and we want to set a breakpoint that is at the location 401260. Then I go to the CPU pane, go to that address is called Control G 401260. Yeah, this one. You go to this one. If you want to see it more clearly, you will see, oops, you can see this function right here. Yeah, this, you go to this. Okay, so it should be okay. Click OK, then we try to click a button right here that create one breakpoint. Then I don't need to see this address. Let me just run it. Then we will see a call function right here. We will call to 401A B 8B. Okay, so before that, must be some push right here. You see the push. This push ESP is 19FB2C to the stack, and then pushing something right here. We don't know what is this. This is referring to a particular address we don't understand. But if we click here, you will see this window will change. That means the content of the ESP plus X in the segment sector will push to the stack. What actual value is it? Its actual value lies in the address 19FB2C. That is right here. Okay, so another push is the pushing something to the stack, and then here is this information at the address 4070A8. Yeah, you can see everything is pushing here. Then we make the call. So this time we won't use the step over. If we want the step over, it will go over here. Everything finished. So this time we want to see what happened inside. So we jump into. Now we have the page aligned with the information state right here. So first thing you see the slide is moving the base pointer, pushing the base pointer to the stack. We don't see anything right here. So, but we will be able to see base pointer in the debugger. 19FF70 will be put it on top of here. Pay attention, step over. See, 19FF70, put it right here. But here is nothing changed. But the stack pointer is changed to this address because something pushed there. The content of stack pointer, of course, changed. Then what is the next? Next is moving the stack pointer to base pointer. Stack pointer to base pointer moving means replacing it. So these two to be the same. Just like here, we do something. Boom, boom. Every two pointer are the same. So let us press the button, and now you will see that there is two output right here, and this is why this is EIP change 2. So EIP right now is ABC. It will change ABE. Now to confirm that, step over ABE, ABE, they are on the same pointer location, just like this. Okay, so nothing changes in the stack, but change in the pointer. Now, the next instruction is to increase the stack pointer by 1C4. Of course, this diagram is not according to the scale, and we need to change the add the 1C4 into here. So the size is 1 to here, but actually add in stack is using the instruction called subtract. The subtract of the base pointer, the adding of base pointer increase to 1C4 by using the subtract argument, the operand. So you will see the operand is larger size. This is the reason why we have the 6 right here. So if we do something like this, this have a significant change. The size of 19FB10 will change a lot. So let us move it, erase to some other location. We are not going back at this moment, but we see that 1C4 increase ESP change in color. It changed to 19F94C. Okay, so that is explaining this slide like this, go to right here, and it will expand the stack frame further. You can have a full picture by checking either on interactive slide, or either you can do it by your own self to study the content about the heaps, and later on complete guide. If you want to go through the PE structure by your own way, you can study the material from other resources other than my lecture. So the stack movement we have already showed you previously. So that calls my talking on the PE format, as well as the stack and calling convention, and by the using the two sample, two binary, bin tags, and Crackme to give you some idea how to use debugger and disassembler. So what is the takeaway? Takeaway is we have some kind of way to perform. If we want to perform the code analysis, we need to have a deep understanding of PE format, and then we use a binary bin text and example to analyze the tool to pick into the PE file, the PF file. Before we perform the code analysis, we have to understand some of the key PE header metadata, which is basically the headers and also sections, and the RVA to raw function. We use the input directory of bin text as an illustrative example, so we can try to demo the relations of raw to RVA to raw, and then VA in the memory doing the PE mapping onto the virtual memory. We discussed the functional core and the stack function by using Crackme. Before the closing, I want to show you the work that I created in 2025. Actually, in year of 2025, I created a document in Word, Microsoft Word. I try to put everything of the bin tags in a form of table. If you want to perform the analysis like me, you can do it by following illustration. Let me close everything first. Okay. Now I put the bin tags into the step PD to allow me to do the analysis. Under the basic bin tags, I put it into the step PD. Oops. Now I have the step P right here, and then I can study the relationship right here. For anything in red, it should be the way that I think they need to be changed into the Lithuanian presentation. So how can I understand what is the size of the DOS header for bin text? So I click the text editor function, and then if I click the DOS header, and yeah, this is the size right here. And then if I want to know what is the size right here, you will see that it's 1 byte. If I block everything, it's supposed 40, not 41, because I add more here. 40 means 64 byte. With the offset start from 0, that is offset, and the end of the offset 3F. So that align with the information right here from offset 0 to 3F, the size 40, which represents 64 byte. Where is the address of the MSAT? Yeah, it's cleared 45A right here. And the document at the here, I try to put the remarks. MSAT is the magic number. So where's the pointer? Point to the PE header. The pointer is at this location, F8, whatever. So that is F8. And F8 is the location you can find the beginning offset of the PE signature. So the same thing, I go to here because P header is combined with two sections. One is the file header. The file header is F8 and then go to F10. It contains 24 bytes. The hexadecimal is 18, and then F8 is changed into pointing to the not FB. I think, yeah, from F8 to FB, it contains the PE, and then an address of the offset from 100 to 103 contain the time value, but we need to do the ending to change it back to the real time for you to decode it. And then at 10C to 10D, 2 byte contain the content of the size of optional header, and then the optional header convert into E0. So two of them adding the optional header plus the file header combined to the result fall into the section of the empty header. Now we go to the directory. Where's the directory? So we go back to the screen of the virtual machine. We have the directory right here. It starts at this location to this end. If we enlarge it, you'll find start from 170 to the address this. So what is the address? I click the icon right here. You will be able to find 1EF. Okay, so if we go to here, you see 1EF, the total directory right here. The export table is 8 bytes. There's 16 of them. So it's 16 times 8 is 128. Okay, so the import address table lies in this location. So we go here, import table at this location. We have the 5C62 representing the pointer of RVA, but this data need to be done with the Lithuanian. So we change it, the data is right here. We change it into this and then RVA. That is the way I change it to find the function name, to find the library name and the first function name. So by the help of the information that I capture in the raw to RVA thing. For example, raw to RVA, if I want to change to 4665, it doesn't work. It's suppose suppose that is 3800 in here. 3800 is the file offset. 3800. So you got the 500 and then we have find the location raw 4656. 4656. You'll find 5C. Maybe I'm wrong. We do RVA should be 6564. 6546. Yeah. We need to do the little ending 6546. We have the 4F46. 4F46. If we using the file inside to find the absolute address of these 4F46, we can find the first function of the API call of the library CTL32DLL. So this is the demonstration for everything, and I hope you like it. And If you may have interest, you can try to do some more thing using my work document, put any binary inside, you do it by your own self and modify and try to using the same tool and methodology to find out the information you want to confirm. If you can confirm everything, then you have a very deep knowledge in the PE format.